Greetings. We have been discussing the Stark effect, and we will continue the discussion of the Stark effect and also begin to introduce the Zeeman effect and the several other phenomena associated with the Zeeman spectroscopy. So, we already found that for the hydrogen atom in the ground state there is no Stark effect in the first order. For the excited state n equal to 2, we know that there is a degeneracy which is 1 over n square, and the consideration of this degeneracy led us to the use of degenerate perturbation theory, and that took us to the family of these linear homogeneous equations which have to be solved, and in these equations you have to determine these coefficients and find the roots, so that you get the 4 different perturbed eigenvalues. They may not however be all different from each other, some of them may still be equal to each other because the degeneracy may or may not be fully removed by this perturbation. So, we have to set up these equations, and for each value of r, and there are 4 of these because there are 4 degenerate states, one is the 2s and then there are the 3 2p orbitals. For L equal to 1 you have m going from -1 to -1, 0 and +1, so there are 3 2p orbitals and 1 2s orbitals, and all of them are degenerate. So, these are the 4 states that we are talking about, and for a particular value of r you can, after getting the roots, you can insert the solution in this equation, and then from this you can find what these coefficients are, but of course you have to find these matrix elements first. So, we began the consideration of determining these matrix elements in our previous class, and this is essentially a space integral over r theta and phi over whole space, and we have in this the cosine theta here, which is coming from z because z is r cos theta. So, this will go into the spherical harmonics and it will have to be included in the integration over theta. There is an r over here, so this together with r square gives you an r cube dr. So, you can separate the radial integral, which is the integration of r cube, and then you have got a theta integration in which you must include this r cosine theta, which is a spherical harmonic for L equal to 1 and m equal to 0 along with this normalization constant. And then of course there is this phi integral, which we discussed in our previous class. Toward the end of the previous class we discovered that this integral will vanish unless m prime is equal to m. So, the only case that we have to consider is that in which m prime is equal to m. Now, if you look at the 4 solutions, the 4 degenerate functions are these. This is the first 1, 2, 3 and 4. Now, out of these 4, which states can give you this possibility that m prime is equal to m, because there is none other which can combine with this or this, and the only 2 states which can combine are the 2s and the 2p0. Okay, so, these are the only 2 states which really need to be considered, because for the remaining 2 you cannot get the possibility that m prime is equal to m, as a result of which those integrals will vanish, the corresponding phi integration will vanish. So, these are the only 2 to be considered for which m is equal to m prime. So, 2s and 2p0 are the only 2 states, the 2p1 and the 2p minus 1 will not enter our discussion. So, out of the 4 states only 2 really need to be considered, and then of course you will have dipole transitions corresponding to delta L equal to plus or minus 1 and delta m equal to 0. Okay. So, these are the transitions, these are the integrals that you have to determine. So, now our problem which had 4 terms reduces to 2, okay, because the remaining 2 do not contribute to the space integral, and now you have got only these equations to be fulfilled. So, there are 2 roots now, there is En1 and you can have 2 solutions for this. So, these are the roots that you have to determine, and from these roots you have to determine the corresponding coefficients CRS, which are the unknowns. So, let us first get the roots. Now, this is a very simple solution, simple determinant to solve, and the roots are given by this when this determinant vanishes. So, this the product of these diagonal terms will give you the square of the perturbation correction, and then you have got the product of these matrix elements which must be subtracted from it, and that tells us that the roots are given by plus or minus square root of the product of these matrix elements, and the product of these matrix elements is nothing but the modulus square, and therefore the perturbation correction is plus or minus the modulus of the matrix element of the perturbation Hamiltonian, which is H1, in the only 2 states which contribute to m equal to m prime kind of situation. So, these are the 2 roots that we get. So, you do not get 4 different eigenvalues, but you get 2 different ones, and the remaining 2 remain the same, they remain equal to the corresponding unperturbed eigenvalue that you had for the Schrodinger equation. So, now you need the matrix element so that you can get the coefficient C. So, let us get the matrix element explicitly. We have already done part of this integration, in which the phi integration we have already carried out, and you have the integration over r, in which you have got an r cube over here. The integration over theta will include this cosine theta which comes over here, and you can plug in the radial functions for 2s and 2p0, these are known. So, you have their explicit form from the non-relativistic Schrodinger equation for the hydrogen atom. So, you put the explicit radial integrals over here and determine this radial integration and the corresponding theta and phi integration. The phi integration is non-zero for m equal to m prime. So, you put in those values, all you have to do is to put these spherical harmonics, and then over here to get this integration over theta. So, this is the integration that you get. So, from the radial integral you get this term after you put in the explicit form of the radial wave functions for the hydrogen atom. So, which is this is the radial integrals, and then from the spherical harmonics you have these terms. This is the spherical harmonic corresponding to L equal to 1, okay, that is the cosine theta term that you are getting. All right. So, what do they give you? After you carry out the theta and the phi integration, this gives you a very simple result, which is minus 3 times the electron charge, the magnitude of the electric intensity, this is the Bohr radius, and then of course the Z. Now, these are the 2 roots that we get, okay. So, plus or minus the modulus of this is just without this minus sign, but then this plus and this minus sign is coming because you have 2 roots, one corresponding to the plus sign and the other coming for the minus sign. So, those are the 2 alternative perturbation corrections that you have got. This is the value of the integral, these are the perturbation corrections, and the 2 roots are minus 3 times E script T A0 by Z, and the other one is the same magnitude but with a plus sign. So, these are the 2 roots that you get. Now, all you have to do now is to insert these roots one by one in this matrix equation, and that will give you the coefficients C1 and C2, okay. So, insert the first root, which is this, which is minus 3E script E A0 by Z. So, this together with this minus sign gives you a plus sign here, and then you have got this matrix element times C2. So, you can see that since this matrix element also has got a minus sign, this equation can be satisfied only if C1 and C2 are equal, right. So, C1 must be equal to C2. So, this is a linear superposition of two states which are the 2s and the 2p0 with equal weights with the same sign. So, obviously when you normalize them, they will each be equal to 1 over root 2. Okay. Now, if you take the other one which is with the plus sign, when you do the same insertion in this matrix equation, you find that these signs, because both these terms now have a minus sign, that requires C2 to have the negative of the sign of C1. So, one will be 1 over root 2, the other will be minus 1 over root 2. Okay. So, those are the two solutions that you get. So, you get one solution which is 1 over root 2 times the superposition of the 2s and the 2p0 state, and the other one is also a superposition of 2s with 2p0, but with a minus sign. Okay. The weight factors are 1 over root 2 in both cases, but in this case the superposition is in phase, in this case it is out of phase. Notice that this is a superposition of L equal to 0 and L equal to 1. So, obviously L is not a good quantum number, and therefore the parity is also not a good quantum number, because it is a mix of 2s and 2p, and this has got some very interesting consequences. So, L is not a good quantum number, but M is a good quantum number because the perturbation Hamiltonian commutes with the Lz, it has got the symmetry, it has got the azimuthal symmetry about the z axis. So, M will be a good quantum number, but not L. So, now you have two frequencies, because the perturbation has given you two additional eigenvalues, which is plus En1 and minus En1, right, and corresponding to these you will get an energy shift, and therefore you will have different frequencies of transitions corresponding to this. So, there will be two additional lines coming out of this. So, these frequency shift is nothing but the energy shift divided by h, and you can also look at the corresponding wave number shift, and you really need strong fields to demonstrate this effect, because the change in wave number over here is relatively small if you plug in all the values, and you need somewhat strong fields to demonstrate this effect. But then if the fields are sufficiently strong, then you can certainly see this effect. So, you get the original eigenvalue, unperturbed eigenvalue, and the M equal to plus 1 and minus 1 continue to have the same energy as the original unperturbed value, but then for M equal to 0 there are two possibilities, one which is psi 2s plus psi 2p0, and the other is psi 2s minus of psi 2p0, both have got M equal to 0. Okay. And these are the two possibilities which have different energies, and you get three energy states from the single degenerate state. So, you get two additional one, and there is one which continues to have the same energy as you had in the unperturbed case. So, the perturbation does not remove the degeneracy fully, it removes the degeneracy only partially, and this situation is very similar to what you would have if you were to place an electric dipole in the electric field, because if you have an electric dipole, it can either take an orientation along the field or opposite to the field or orthogonal to the field, right. Or when you have it an orthogonal to the field, you do not have any energy difference. So, this energy correction is then effectively completely equivalent to the energy of a dipole moment interacting with the applied electric field through this interaction d dot E, which is the classical expression for the interaction of an electric dipole with electric field. And for n equal to 2 state, the hydrogen atom in the excited state, which is the n equal to 2 state, it behaves as if it has got a permanent electric dipole moment, okay, which is given by this 3 E A0. So, that will be the value of the dipole moment for the hydrogen atom in the excited state. For the ground state, of course, there is no Stark effect and the corresponding dipole moment would be 0. So, there is no permanent dipole moment for the hydrogen atom in the ground state, but for the first excited state, which is n equal to 2, it does have a permanent dipole moment. Now, of course, we have made some approximations. There are some additional factors to be considered. You have to consider the fine structure, you have to consider the Lamb shift, and there will be some corrections due to that. So, as a result of these, 2s and 2p are near degenerate, 2p has additional splitting, which is the spin orbit splitting. So, there are some additional details to be plugged in, and there are other interesting consequences of the mixing of the 2s and 2p state. It affects the lifetime of a state, and you will remember that we discussed this in our earlier unit, that the excited state has got a certain lifetime because of spontaneous emission, and this is determined by the Einstein coefficient AJI. So, we discussed this in our previous unit, and the rate of change of the population in an excited state is then governed by this exponential law, in which you can have decays to all states I which are lower than Ej. So, there will be a spontaneous emission possible to all possible states. So, Ej, if n is equal to 2, there is only one state, but n could be higher than 2 when you take n equal to 3, 4, 5 and so on. So, for any excited state you can have spontaneous emission to lower states, provided selection rules permit them and so on, other conditions have to be satisfied, and we discussed this in our unit 7. So, this exponential law gives you this lifetime tau, which is the inverse of the Einstein coefficients, but you must sum over all the Einstein coefficients if there is more than one transition that is possible. So, this lifetime will give a certain width to the excited state, which is responsible for the width of the excited state according to the uncertainty principle, but this is, as we discussed earlier, this is not because there is an operator for time which does not commute with the Hamiltonian, that is not the reason, but because of the interaction of the quantum system with the rest of the universe, which is unspecified degree of freedom in our problem. So, there is a corresponding width which is delta E, which goes as the inverse lifetime, and these lifetimes are of the order of few nanoseconds, okay, that is the typical lifetime magnitude. But then of course, when you have an ensemble of hydrogen atoms, this lifetime can actually be reduced further because of collisions, and there are if two hydrogen atoms collide with each other, then it can reduce this lifetime compared to what you get from the consideration of a single hydrogen atom like this. Now, in addition to this, from the Stark effect that we have just discussed, we find that the 2s state acquires a little bit of 2p character because of the Stark effect. Okay, so, the 2s state is not a pure state anymore, it develops a 2p kind of character. So, the 2s to 1s normally you will not have a dipole transition because that is a delta L equal to 0. So, that is a forbidden transition typically, but because the state is now mixed with 2p, then you can have a radiative transition from the mix of 2s and 2p to the 1s, and because this additional decay pathway, a radiative decay pathway is opened up, it reduces the lifetime. So, the hydrogen atom in the electric field in an excited state will have a slightly lower lifetime than what a hydrogen atom which is not in an electric field. Okay. So, it causes a little bit of reduction in the lifetime. This is a transition which is enabled by the mixing of 2s and 2p. This is not a parity violating transition which comes because of the weak interaction. So, that is also possible, but that is a different channel altogether. So, you can extend this analysis to higher excited states like n equal to 3, and like n equal to 3 you will have degeneracy which goes as 1 over 3 squares. So, there will be 9 degenerate functions. So, 3s, 3p, 3d they will all be degenerate, and then L is not a good quantum number as we have already seen. So, you will have various possibilities. So, the degeneracy will be removed partially, but not fully, and you can carry out a similar analysis and extend it to Stark effect of higher quantum numbers. Now, we will introduce the discussion on the Zeeman effect. Okay. Now, we consider the atom in a magnetic field, and then there are 3 different phenomena that one talks about, which is the normal Zeeman effect, the anomalous Zeeman effect, and also what is known as the Paschen-Bach effect. And typically the normal Zeeman effect is what you refer to when you are dealing with strong magnetic fields. The anomalous Zeeman effect when you have weak fields, it is not really an anomalous, it is in fact quite a common phenomenon, but it is called as anomalous because historically it was observed at a time when the electron spin was not known. So, everybody suspected that there is some anomaly in the Zeeman effect. So, that is the reason it was called as anomalous Zeeman effect, and for historical reasons these names have persisted, but it does not mean that there is any real anomaly associated with the so called anomalous Zeeman effect. Again, when you talk about weak fields and strong fields, these are qualitative terms, and we will have to get some idea of what we mean by strong fields and what we mean by weak fields. So, it is in relation to some other interactions that you will call them as strong or weak, and this will become clear as the discussion progresses. So, Zeeman effect was first observed by Peter Zeeman in 1896. I think he got the Nobel Prize which he shared with Lorentz. And if you now consider an atomic field which is homogeneous over the atomic dimension, then the corresponding vector potential can be written as this, because this is the usual well known form from classical electrodynamics that you know, that this vector potential gives you a constant homogeneous field, right. So, this is the vector potential that we will use, and with this vector potential the generalized momentum will take this form P minus E A over C, which we have discussed earlier as well. So, this is the generalized momentum that should go into your Schrodinger equation, it will go into your Hamiltonian, and with this Hamiltonian you will have 2 terms P dot A and A dot P, but P is a momentum operator. So, you have got the del dot A and the A dot del terms, okay. And when you operate by A dot del and del dot A on an arbitrary function, you get twice A dot del in the Coulomb gauge, right. So, we have used this result earlier as well, and we can put in this form in the Schrodinger equation. So, this is what we have got. So, from these 2 terms we get the twice A dot del, but there is a 1 over 2 m here. So, the 1 over 2 cancels this 2, and you have got this minus I E h cross over m c A dot del coming from this term, and there is of course a quadratic term coming from A dot A, okay. So, this is the Schrodinger equation that we have to deal with. Now, in this relation the vector potential has got this form. You know that this is the correct form because if you take its divergence it vanishes, if you take its curl you get the correct magnetic field, okay. So, this is the appropriate vector potential to be considered, and if you put in this vector potential in this A dot del, then you have got this A is replaced by half B cross L, B cross R. So, you have got a triple product here, cross and dot can be interchanged. So, you have got a B dot R cross gradient term, and if you take this minus I h cross along with the gradient operator, you recover the momentum operator, but you have got a minus sign coming from here. So, you can you notice that this is B dot r cross p or B dot L. Okay, r cross p is the angular momentum operator. So, you get the angular momentum operator B dot L, and this operator will be of order E b over twice m c multiplied by the order of the angular momentum, which for our consideration we take to be of the order of the Planck's constant. Okay. So, that is the order of magnitude of this term. To get an estimate of how strong this perturbation is, all we have to do is to consider the magnitude of B, and then you already have the 1 over 2 m c term, and the angular momentum is of the order of the Planck's constant, and you have another term over here which is the quadratic term, which is E square over twice m c square, and this term E square over twice m c square a square. So, this is the A is half B cross r. So, you have A dot A. So, you take the dot product of these two vector potentials, and B cross r will give you the B square r square sine square theta. Sine square theta is of the order of 1, that is right, and this is of the order of B square. So, if you take the ratio of the quadratic term to the linear term, it is of the order of B. So, unless B is really very strong, this is not going to be important. You have got the Planck's constant and the speed of light sitting in the denominator, and unless B is really very strong, this term is not going to be important. So, this is the consideration that I had hinted at, that when you talk about strong fields, you have to keep in mind what kind of magnitudes are you talking about, and you really need very strong fields to look at quadratic terms, and those are not the magnitudes that we are going to be concerned with in the laboratory magnetic fields. So, this term can be ignored. You usually have rather weak fields, but within this domain of weak fields, which is weak enough so that the B square term can be ignored, within this range of course you have a still consideration of how strong the field is within the small weak range. Okay. So, we will get into these details. So, now we have thrown the quadratic term, and you have only the linear term, which is B dot L, and B dot L term, now does it not look like the interaction between a magnetic dipole and a magnetic field, right? Because if you keep a magnetic field in a magnet in a magnetic field, it will have an energy mu dot B. This is just what we did in the Stark effect. When you put an electric dipole in the electric field, it gave you a perturbation energy of D dot E. So, similar to that, where D was the electric dipole moment. So, now you will have the magnetic dipole moment, and you can expect a similar form developing from this expression of B dot L, and this is what you can treat perturbatively, because these two terms give you the unperturbed Hamiltonian for which the exact solutions are known, and then you can treat this perturbatively because B is small. Okay. So, this is like a mu dot B term, and to write this in a form which is like mu dot B, you recognize that there is a magnetic moment which is associated with this orbital angular momentum vector. Okay. So, this orbital angular momentum vector L must be associated with a magnetic moment, and that magnetic moment is mu L, which is given by minus, it is proportional to L over H cross. The proportionality is what is called as a Bohr magneton, and this is the perturbation Hamiltonian that you should insert in your Schrodinger equation and then treat it using usual perturbation theory. So, which is what the task of the Zeeman effect is. So, this is the Zeeman effect perturbation corresponding to the interaction of a magnetic dipole. This is coming from the orbital angular momentum, and this is represented by this L prefix. This is coming from the orbital angular momentum. Okay. And notice that in addition to this orbital angular momentum, the electron has got an additional source of angular momentum, and this is something which was not known in the early days of quantum mechanics. This was recognized by Uhlenbeck and Goudsmit when they did their experiments in the laboratory of Paschen, and what they found was some additional lines which are normally forbidden, and because of these forbidden lines they had to associate an additional source of magnetic moment for which they looked for an additional source of angular momentum. So, that is how they introduced the electron spin historically, and this was an accident because they really did not know the exact source of this magnetic moment. So, they introduced it because the orbital angular momentum of course could be associated with a magnetic moment. You get it also from your classical idea that if you have got an electron which is revolving in a circular orbit and this is the direction of its angular momentum, then the conventional current flows in the opposite direction, which is this red direction, right, and the conventional current goes in the opposite direction. It has got a corresponding linear momentum which is in the opposite direction as the linear momentum of the electron itself. Okay. So, now you have got a charge in motion, a current in motion, and you know that if you just use your classical electrodynamics, you know that it generates a magnetic field as if there was an electric dipole, right, because you have got a current carrying loop and it would generate a corresponding magnetic field as if it is generated by an electric current. This current is charge over time, so it is velocity over the circumference of the trajectory of the electron. So, that is the classical from the semi classical model of Bohr theory that you can come up with this idea, and the corresponding magnetic moment is nothing but the current times the area, as we know from classical electrodynamics, right. So, you have got a 1 over c here because you are using the Gaussian CGS system of units, and the SI it is just IA. So, you have got the magnetic moment which is IA, and it has got the direction which is opposite to that of the orbital angular momentum of the electron, because the conventional current is in the opposite direction. So, this is the magnetic moment that you get, and this magnetic moment I is the current which is EV over 2I pi r. So, you put I over here, the area is pi r square. So, you get E over 2 C times VR, and VR is nothing but the magnitude of the cross product V cross R. Okay. It is nothing but the magnitude of V cross R. So, V cross R is the same as P cross R by M. So, you get the angular momentum divided by M coming out of it. So, you find that there is a magnetic moment associated with an orbital angular momentum, but the sign is negative over here, okay, because this A and mu have got opposite signs. You have already seen it over here that the angular momentum has got this sign and the magnetic moment has got the opposite sign. So, there is a minus sign over here. So, this magnetic moment is proportional to the orbital angular momentum vector, and this is the proportionality, and you can write this, you can multiply this factor by h cross and divide this by h cross. So, you can write this angular momentum in units of h cross, essentially that is what you have done. What it gives you is the proportionality which is referred to as the Bohr magneton. So, this is the EH cross over twice MC, this is the Bohr magneton. There is an additional factor G which is introduced, which is in this case equal to 1, and we need not worry about it at this stage, but it becomes relevant only in the context of the magnetic moment coming from the electron spin. Okay. So, as Uhlenbeck and Goudsmit found that there is an additional source of the angular momentum. So, this angular momentum will give you an additional magnetic moment mu, which can again be written as proportional to S over H cross with the Bohr magneton, but now the proportionality is not just 1, it is 2, because the G for the electron spin is 2, and we get this from the Dirac equation. We have seen this explicitly in unit 3 when we did the Foldy-Woodhuizen transformations, and in the Foldy-Woodhuizen after 3 Foldy-Woodhuizen transformations we get the exact spin orbit term, and we find that it corresponds to a magnetic moment of the electron given by the electron spin, and then the corresponding G value is 2. So, it is in the context of G for electron spin equal to 2 that G equal to 1 for the orbital angular momentum becomes relevant. So, this is the net magnetic moment which should come from two sources, one is the orbital angular momentum and the other is the spin angular momentum, and together with this L and S, L scaled by GL equal to 1 and S scaled by GS equal to 2, along with these you have a net magnetic moment which you should now be using, and we had considered earlier only the angular momentum coming from the orbital angular momentum quantum number. So, now this relation in which we decided to treat mu dot B as a perturbation must now include the spin. So, this mu is not just mu subscript L, but the mu together with the electron spin. So, this mu is minus mu B, which is the Bohr magneton, times L plus 2s over h cross, where s is h cross over 2 times this is the Pauli vector sigma, right. So, you have got this minus mu dot B term instead of minus mu L dot B term. So, there is an additional component over here to include the magnetic moment of the electron spin, but then there are other perturbations. Now that the electron spin is there, the electron spin will couple to the angular momentum, because S dot L interaction cannot be ignored when it is of the same magnitude as mu dot B, right. So, all consequences of the electron spin now have to be taken into account, because you cannot do it piecewise. So, the moment you include the electron spin, you must also include the spin orbit interaction, which we know again from which is the spin orbit interaction, and this spin orbit interaction again we had the explicit form of this from the Foldy-Woodhuizen transformations. This form becomes manifest. It goes as S dot L, and then you have got the 1 over r del V by del r coming from the rate at which the potential changes with distance. So, for a 1 over r potential it goes as 1 over r cube. So, now these are the two terms, the minus mu dot B and the spin orbit interaction. These two are to be considered together in Zeeman effect. Okay. So, Zeeman effect is an interplay of these two terms which contribute to the perturbation. The rest of the Hamiltonian, which consists of the kinetic energy part and the potential energy in the field of the nucleus, these two terms constitute the unperturbed Hamiltonian, and then you have perturbations due to the magnetic moment in the presence of the magnetic field, but this magnetic moment has got two origins, one from orbital angular momentum, one from the spin angular momentum, and then there is an additional term which is the spin orbit interaction. So, this is the Zeeman effect perturbation that we have to refer to. Okay. Now, we have to deal with various situations, because when you are considering two contributions to the perturbations, then you have to take into account the more important term first and the less important term next, or else if they are both of the same order, then you have to take both of them into account together, and that is going to depend on the strength of the magnetic field. The S dot L term, the spin orbit interaction, is internal to the quantum system. The quantum system exists along with this interaction, you have no control on that. The external magnetic field is that you can control, you can set it equal to 0, you can slowly increase it, you can make it equal to a certain magnitude, cross that you can make it very strong, okay, and then you have a qualitative control on that which you can call as weak, moderately strong, very strong, and so on. So, that is something on which you have got a control on. You have no control on the magnitude of the spin orbit interaction which is internal to the quantum system. So, there are three cases to talk about. One in which the magnitude of this field is such that this term will be stronger than the spin orbit interaction. Okay? And when you have this situation, you refer to the phenomenon as what it was historically called as the normal Zeeman effect. It does not mean that other cases are abnormal or anything like that, but only that this is called as the normal Zeeman effect because this was seen before physicists reconciled with the electron spin, and this is what is called as the normal Zeeman effect. This requires strong field in the sense that this term is more important than the spin orbit term. Okay, that is the meaning of a strong field, but it is not so strong that you have to include the quadratic terms b square. Okay, we have already discarded those terms in b square. So, it is not strong enough to consider the b square terms, but it is referred to as a strong field effect only because it is stronger than the spin orbit interaction. So, it is only with reference to the spin orbit interaction that you call this as a normal Zeeman effect, and then you have the second case in which these two are roughly of the same order. Okay. So, you cannot throw one and keep the other, and then you have to consider both of them together, and these are the details that we shall be considering in the next classes. So, this is the case in which you have the two terms which go into the perturbation which are roughly of the same order. Nevertheless, the magnetic field is slightly larger than to make this term, the mu dot b term, a little more important than the spin orbit interaction. Okay. So, this is the case which is called as the Paschen-Bach effect, corresponds to intermediate magnetic field, and the third case is the weak field case in which the mu dot b, because b is weak, this term is much weaker than the spin orbit interaction term. So, this is what is called as a weak field term in which the spin orbit interaction becomes the dominant perturbation, and this is called as the anomalous Zeeman effect because it was discovered during the days when the electron spin was not known. So, it was seen as an anomaly. So, we are going to use perturbation theory to resolve this situation, and we know, as we discussed earlier in unit 5, that you can have a perturbation due to a variety of causes. You may have internal causes, external causes, and you may have various kinds of magnitudes of internal causes plus external causes. Okay, we have not even considered all internal causes yet. For example, there is the nuclear spin, and you can consider the hyperfine interaction which comes as a result of the nuclear spin. So, that is yet again an additional internal perturbation that can be taken into account, which we will talk about a little later. But then the external fields again you can have different kinds, and then the important thing in perturbation theory is that larger corrections must be included first, the weaker corrections to be included later, and all corrections which are comparable to each other must be considered together. So, these things we discussed in unit 5 as well, and there of course are additional factors like I mentioned. You have got the hyperfine structure, you also have the Lamb shift, and then you have the Stark effect and the Zeeman effect, which are examples of external perturbations on which you have some control in the laboratory. So, those considerations lead us to the determination of the perturbation correction, which is given by the usual form of the first order perturbation theory, that the first order perturbation correction will be given by the matrix element of the perturbation Hamiltonian in the unperturbed state. And now these states are described by the quantum numbers which are eigenvalues of the operators which commute with each other. So, this gives you a complete set of commuting operators. These are good quantum numbers, but then you also have an alternative set of quantum numbers because of the spin orbit coupling. And a question that we discussed in unit 5 was, which set are you going to use? Will you use this set or will you use this set? And this is what Zeeman spectroscopy is about, okay? Because the set the basis set which is appropriate for the normal Zeeman effect need not be appropriate for the anomalous Zeeman effect, it need not be appropriate for the Paschen-Bach effect, and in each case you have to make your choice very carefully, and these are the details that we will be discussing in the next few classes. So this is the cardinal rule which we refer to in unit 5, that you must choose the unperturbed kets which diagonalize the perturbation, but then how this is done specifically in the normal Zeeman effect, in the anomalous Zeeman effect, and in the Paschen-Bach effect is a matter of detail, and this is something that we will discuss in the next few classes. If there is any question for today, I will be happy to take. Yes? If there is no question, goodbye for now.